Now that we've covered naming, we can go ahead and start putting these compounds together. So the first thing I want to look at is percent composition of the compounds. What in the heck do we mean by percent composition? What I mean by that is how much of the compound is made up by the mass of one species versus how much of the compound is made up by the mass of another species. Recall your junior high definition of percent. Percent is your part divided by the whole times 100%. When we refer to percent composition, we mean percent by mass, not percent of what element we have to each other. What do I mean by that? Let's look at this example. What is the percent hydrogen in water? There should be a letter D here. I apologize. Every time I fix this, I forget to save the file correctly. But the percent hydrogen in water, is that 11.2%, 33.3%, 50%, or 66.7%? A number of students, when they think about percent composition, they would say, well, you've got water is H2O, so I've got 2 hydrogens compared to 3 atoms times 100%. That is not correct. It's not correct because that's not based on mass. We want to know the percent composition, but we're not going to specify percent composition is actually by mass. We're not going to explicitly state that, but we need it by mass because we can do a series of analyses to determine empirical formulas of compounds. There's a number of experiments we can do. Again, if you take Gen Chem 1 lab, you're going to do this at your very first lab. We can do an experiment to figure out the empirical formula, which can lead us to the overall formula, but it is based on mass. So we need to know the percent by mass. So in this case, the way I figure this out is I want to know the percent hydrogen would be the mass of hydrogen in the compound compared to the total mass of water times 100%. I know to figure this out, I'm going to say percent of hydrogen. Water has 2 hydrogen atoms, and each hydrogen atom contributes 1.008 grams per mole to the overall compound. I know water, you guys can add up molar masses. Water has a molar mass of 18.02 grams per mole. And I'm going to multiply this by 100%. Note that my units cancel out here, so I don't even have to worry about units anymore. It's truly just a percent. And this will equal out to a value of 11.2%. So when I say what is the percent composition of hydrogen in water, the answer is 11.2% because it's by mass. About 11% of the mass of water is actually due to the presence of hydrogen. The other roughly 89%, 88.8% is actually due to oxygen. That's just because oxygen is a lot bigger than hydrogen. Hydrogen is the smallest atom we have. So what is the percent nitrogen in ammonium phosphate? In order to solve this problem, we first need to figure out the formula of ammonium phosphate. But now that we know naming, we can quickly do that. We know ammonium is one of our polyatomics with the formula NH4+. Phosphate, also a polyatomic with the formula PO4 3-. If I cross charges here, I see that I need 3 ammoniums for every 1 phosphate. So my formula will be NH4 3PO4. Next thing I need to do is find the molar mass of the entire compound. So you need to recognize that you have 3 nitrogens, 12 hydrogens, 1 phosphorus, and 4 oxygens to make up this total compound. When you add it all up, the molar mass will equal out to 149.0 grams per mole. And again, that is for ammonium phosphate. But I want percent nitrogen. So I need to take the mass of just nitrogen divided by the mass of the total compound. I have 3 nitrogens, and nitrogen has an atomic weight of 14.01 grams per mole. The total compound has a molar mass of 149.0 grams per mole. Note, this cancels out my units, so I don't even have to worry about those. And this is times 100%. This gives me an overall answer of 28.1%. What that means is if I have a sample of ammonium phosphate, About 28% of it is due to nitrogen. The mass of 28% of it's due to nitrogen. I'm going to take advantage of this, and the very next part we're going to do here in this video is empirical molecular formulas. We're going to use this to our advantage to figure out the overall formula of compounds when we've analyzed them but maybe don't know what their original formula was. So, empirical and molecular formulas. What is the difference here? A molecular formula is something that shows the number of atoms of each element in a molecule. So, molecular formulas can match empirical formulas, but they don't have to. What I mean by that is NaCl is an empirical formula. I'll talk about why in a sec, but it also exists as the formula unit for NaCl. NO, nitrogen monoxide, that is a molecular formula and an empirical formula. NO2, molecular formula, empirical formula. But N2O4 is just a molecular formula. It is not an empirical formula. So here we see as an example, the molecular formula of benzene is C6H6. An empirical formula, the difference between these is while molecular formula shows you the actual formula, how many of every single atom do I have in that formula, an empirical formula shows us the smallest whole number mole-to-mole ratio of the elements in a compound. And this is what I want you to remember. I want you to remember this terminology, smallest whole number mole-to-mole ratio. Because if you can remember that, you can do any empirical formula problem without any issue. You need the smallest whole number ratio, and they need to be mole-to-mole ratio. So you got to convert to moles. But what does that mean? What's the empirical formula of benzene? The molecular formula is C6H6. Empirical formula, though, is the smallest whole number mole-to-mole ratio. This is telling me that I have 6 moles of carbon to every 6 moles of hydrogen. But the smallest whole number ratio would be CH. So CH is the empirical formula of benzene, whereas C6H6 is the actual formula of benzene, so therefore the molecular formula of benzene. Let's work some examples on figuring these out. Suppose that a compound with an empirical formula of CH2O has a molar mass of 120 grams per mole. What is the molecular formula of this compound? How are you going to figure this out? The way I want you to figure this out is I want you to first find the mass of the empirical formula. So if I've got 1 carbon, 2 hydrogens, and 1 oxygen. If I add this up, this is approximately 30 grams per mole. You've got 12.01 plus 2.016 plus 16. It's basically 30 grams per mole. My molar mass, the entire compound actually weighs 120 grams per mole. So I'm going to say 120 grams per mole divided by 30 grams per mole gives me a value of 4. What that means is the molecular formula has a ratio that is has the ratio empirical formula of CH2O, but it's actually 4 times larger in mass, which means whereas my empirical formula is CH2O, my molecular formula would be 4 times that. So C4H8O4. And if I added up the molar mass of this, I would find it to be approximately 120 grams per mole. So this 4 means I'm going to take this and multiply the empirical formula by that ratio. So 4 times CH2O, which will give me C4H8O4. That's great. And it's great to know that if we know the empirical formula. But what if we don't know the empirical formula? Then we first have to find the empirical formula. So an empirical formula, again, and this is what I absolutely want you to use and remember, it's the smallest whole number mole-to-mole ratio of the elements. And I harp on that because if you can remember the smallest whole number multiple ratio, if you get stuck, you're going to think, okay, I need moles. Okay, now I need a ratio. What's my smallest whole number ratio? I'm going to take a bigger number and divide it by a smaller number. And I'm going to show you all this in an example in just a sec. But if you can remember that definition, I think it will help you. Remember that percent composition is percent by mass. This can help us. If you're given the percent composition and molar mass, the problem's even easier. You can start with 100 grams of unknown, or you could start with 1 mole. So we're going to see examples here where we can start with 100 grams of unknown. We can assume we have 100 grams, so we have a percentage. We could also start with 1 mole if we needed to. There's a lot of different ways we can do these, but let's go ahead and look at some examples. What is the empirical formula of a compound that consists of 52.13% carbon, 13.14% hydrogen, and 34.73% oxygen by mass? How do I know it contains this? Because I've done some kind of experiment that led me to determining how much carbon, hydrogen, and oxygen I had in the overall mixture. If you look at this, 52.13 plus 13.14 plus 34.73 equals up to 100%. When that happens, what I want you to do is assume. I know we never say assume. In this case, you're going to assume. You're going to assume that we have a 100-gram sample. If we have a 100-gram sample, that means that I have 52.13 grams of carbon. I have 13.14 grams of hydrogen. I have 34.73 grams of oxygen. I need their smallest whole number multiple ratio. To get to there, I need to take these grams and convert them to moles. So for carbon, 52.13 grams of carbon converted to moles. I expect that to be a little over 4 because I know 4 times 12 is 48. And I find the answer here to be 4.341 moles of carbon. Hydrogen. I expect this to be around 13 because I know hydrogen has a molar mass of about 1.008 to be exact. This equals out to 13.04 moles of hydrogen. And oxygen. I expect this to be around 2 moles because I know that oxygen has a molar atomic weight of 16 grams per mole. 34 is a little higher than 16 times 2. And I find moles of oxygen here to be 2.171 moles of oxygen. The next thing I want you to do is look and see which one is the smallest number. Because we're going to divide all of them by the smallest number because, again, we want that smallest whole number ratio. When I look at these, I see this is the smallest number. So I'm going to divide everything by the number of moles of oxygen. Carbon, 4.341 moles of carbon divided by 2.171 moles of oxygen gives me an answer of 2.002. I'm going to round this to 2 because I need a whole number. That means that I have 2 carbons for every 1 oxygen. Do the same thing for hydrogen. 13.04 moles of hydrogen divided by 2.171 moles from the oxygen gives me an answer of 6.006, which I'm going to round to 6 because I need whole numbers here. And lastly, for oxygen, of course, 2.171 moles of oxygen to 2.171 moles of oxygen gives me 1. What this means, though, is that for every one oxygen, I have 2 carbons and I have 6 hydrogens. This is my empirical formula. C6 or C2H6O. For every 1 oxygen, I have 2 carbons and 6 hydrogens. Let's do another example. A certain compound consists of 38.70 grams, or 38.70% carbon, 9.74% hydrogen, and 51.56% oxygen by mass. The molar mass of this compound is 62.07 grams per mole. What is the molecular formula of this compound? How am I going to find that? I'm given a piece of information to figure out the empirical formula. I'm also given the molar mass. So I'm going to use this information to get me to the actual molecular formula. So carbon, let's first do carbon. Carbon, I'm going to assume again 100 gram sample. There's 2 different ways we can do this problem. I'm going to show you both ways. First way we're going to do it is like the previous example. 38.70 grams of carbon. Convert that to moles of carbon. And I need to calculate this out. I apologize. I forgot to write this down. 38.7 divided by 12.01 gives me an answer of 3.222 moles of carbon. Hydrogen. 9.74 grams of hydrogen. Convert that to moles of hydrogen. 1.008 grams of hydrogen per mole. Gives me 9.663 moles of hydrogen. And for oxygen, 51.56 grams of oxygen. Convert that to moles of oxygen. There's 16 grams of oxygen for every mole. Gives me 3.223 moles of oxygen. Now I'm going to divide them by the smallest number. Now, technically I see that carbon here is the smallest number, but they're basically equivalent, but we can still go ahead and divide by everything by carbon. So for carbon, I'm going to take 3.222 moles divided by 3.222 moles. And I see, of course, it's an answer of 1 here. For hydrogen, 9.663 moles of hydrogen to 3.222 moles of carbon. And I know the answer will be 3. I don't know. I'm sure we have to round it. It's probably 2.9 something, but it's basically 3. Let's see, 9.663 divided by 3.222. Yeah, it gives me 2.999, but that basically, we have to round that up to a whole number, so 3. And then for oxygen, 3.223 moles of oxygen to 3.222 moles of carbon. I know it's 1, but if I actually calculated that out, I would see, well, it still rounds to 1 for 4 sake things, 1.0003, which would be 1.000. So 1. What I see here, though, is that my empirical formula is equal to one carbon for every 3 hydrogens and 1 carbon for every 1 oxygen. So CH3O. Now I need some space here, so I'm going to erase this. But I'm not done with the question. I want to know the molecular formula. What I could do now is I could add up the molar mass of this compound. So the molar, of this empirical formula, the molar mass of CH3O, 12.01 plus 1.008 times 3 plus 16 is going to give me 31.03 grams per mole. I know the molar mass of the actual compound, call that X, is equal to 62.07 grams per mole. I'm going to divide this by the molar mass of the empirical formula. And I see the answer here is basically 2. It's not going to be an exact 2. Well, when I round, it gives me 2.0003, so I would round it to exactly 2. What that means, though, is that the molecular formula is 2 times that of this empirical formula. So C2H6O2 is my molecular formula. There's a faster way we can do this, though. So if you need to write this down, pause the video, but I'm going to erase all this because I'm going to show you the faster way to do it. This way is fine. You're welcome to do it this way, but the other way is a little bit faster. In this case, because I am given the molar mass of the entire compound, I can assume that I have 1 mole of your unknown. I know that 1 mole is equal to 62.07 grams of unknown. Now I can go ahead and figure out if I know that I have 62.07 grams of unknown. I know 38.7% of that is due to carbon, 9.74% of that is due to hydrogen, and 51.56% of that is due to oxygen. So the number of moles of carbon, I'm going to say 0.3870 times 62.07 grams. This is going to give me the mass just due to carbon. I'm then going to convert that to moles of carbon. And this gives me 2 moles of carbon. So if 38.7% of it is due to just carbon, that's the same as saying 0.387 times 62.07 to get the actual mass of carbon. I convert that to moles, and I see that that amount equals out to 2 moles of carbon. Number of moles of hydrogen, 0.0974 times 62.07 grams for the entire compound. Again, this gives you the mass of the entire compound that's due to just hydrogen, but mass is in grams. I need moles for the formula. So I'm going to say times 1 mole of hydrogen divided by 1.008 grams of hydrogen, and this mass equals out to 6 moles of hydrogen. Lastly, oxygen. Number of moles of oxygen, 0.5156. 51.56% is 0.5156 in fractional form times 62.07 grams. This is due to the mass of oxygen. Now I've got grams of oxygen. I'm going to figure out how many moles that is, times 1 mole of oxygen to 16 grams of oxygen. This equals out to 2 moles of oxygen. So this, because we assume we have 1 mole, if I'm given the molar mass, I can assume 1 mole. This is just a faster way, gets me to the same point, and it tells me 2 carbons, 6 hydrogens, and 2 oxygens for the overall molecular formula. Again, you're welcome to do it the other way if you're more comfortable with that way. This is just, if you're given this molar mass, you can do it this way as well. The other thing we need to talk about here is combustion analysis. Combustion is when I burn something, and I can burn something and then use that information I get. I can analyze what comes off of it to figure out what the original formula of something was. In combustion analysis, carbon is converted to CO2. All carbon, all of the carbon in the sample is converted to CO2. So we can use the mass of CO2 to find the moles of carbon. All of the hydrogen in the sample is converted to H2O. So carbon to CO2, hydrogen to H2O. So we can use the mass of water to find the moles of hydrogen that we originally had. Oxygen is added in excess. To determine the moles of oxygen in the compound, we're going to subtract the masses due to carbon and hydrogen from the mass of the original sample and then convert that mass to moles of oxygen. Nitrogen can be determined by ammonia production of a separate sample, and other elements can also be analyzed in a similar fashion. So this is a nice flow chart from your textbook to follow through how to do combustion analysis, empirical formulas and whatnot with combustion analysis. So you're welcome to read through this if you would like. It does gives you a great way to describe through it. Go ahead and pause the video and read through that, or just look in your textbook and find the figure there as well. But let's go ahead and work an example. So let's look at an example. Now, there are more examples in your notes, in the additional practice notes, in your textbook, in your homework, etc., in your online homework, whatever you need. Here, I'm going to work one example with carbon, hydrogen, and oxygen, but again, please check out the additional practice because I do examples with more than just these three elements in it. And you need to see how to do it with more than just three. So here, an unknown compound consists of carbon, hydrogen, and oxygen. When a 1.125 gram sample of the unknown was analyzed by combustion analysis, 1.649 grams of CO2 and 0.675 grams of H2O were formed. If the molar mass of this unknown is 180.2 grams per mole, what is the molecular formula? In combustion analysis, again, we've learned about this, but in combustion, we know that we've got some kind of carbon, hydrogen, in this case, carbon, hydrogen, oxygen containing compound. It reacts with oxygen and it forms CO2 and water. We want to figure out what is X, what is Y, and what is Z. I know that I'm just looking at carbon, hydrogen, and oxygen. I know that I have a 1.25 gram original sample. I know it produces 1.649 grams of CO2 and 0.675 grams of H2O. I know that its molar mass is 180.2. So first, let's figure out the number of moles of carbon. I've got 1.649 grams of CO2. I'm going to convert that to moles of CO2. There's 44.01 grams of CO2 per every mole. And I know that for every 1 mole of CO2, there is also 1 mole of carbon. This gives me 0.03747 moles of carbon. Because I'm going to need it, I'm also going to figure out how many grams of carbon does this equal. So if I took those moles and converted them to grams of carbon, I know there's 12.01 grams of carbon to every 1 mole of carbon. Why do I need this? Because I need to figure out how much oxygen I have. And this shows me how much of this original sample was actually just due to carbon. I know what the remainder of it is due to hydrogen and oxygen. I can figure out the mass of hydrogen as well, so therefore I can figure out the mass of oxygen. So let's look at the number of moles of hydrogen. All hydrogen, as all carbon was converted to CO2, all hydrogen was converted to H2O. I have 0.765 grams of H2O. I know that there are 2 moles of hydrogen for every 1 mole of H2O. I apologize. I forgot I need to convert that first. It helps when these are in moles. I cannot do that without putting these in moles first. So 1 mole of H2O contains 18.02 grams of H2O. Now I can convert to moles of hydrogen. I was a step ahead of us. Also, if you always want to check grams of CO2, moles of CO2, give me moles of moles of carbon, grams of H2O, moles of H2O, give me moles of hydrogen. This gives me 0.0749 moles of hydrogen. Note, here I had 4 sig figs, so I'm keeping 4 sig figs here. Here I had 3, so I'm keeping 3. As before, I'm also going to figure out what is the mass of this many moles of hydrogen because I will need it to figure out the mass of carbon in the original or mass of oxygen in the original sample. So this gives me 0.0755 grams of hydrogen. Now I know the moles of carbon and mass of carbon and moles of hydrogen and mass of hydrogen that I had in the original sample. I want to find the mass of oxygen. I know that the mass of my unknown sample is equal to the mass of carbon plus the mass of hydrogen plus the mass of oxygen. Therefore, the mass of oxygen has to equal the mass of the unknown minus the mass of carbon minus the mass of hydrogen. I'm looking for grams, so the grams of oxygen will be equal to 1.125 grams of sample minus 0.4500 grams of carbon minus 0.0755 grams of hydrogen. I find the mass of oxygen to be 0.5995 grams. It's the only way I know how to find the mass of oxygen. I know all three have to add up to the original sample. I've been able to figure out how much carbon do I have, how much, this should be a C here, I apologize. I know, sorry, I'm writing this wrong. I'm thinking ahead and I should stop thinking ahead. This is mass of oxygen. So I know the mass of carbon, I know the mass of hydrogen, now I know the mass of oxygen. Now I did run out of room and I'm going to have to erase in a sec, so please pause the video if you need to write things down now. But I do need to remember, I'm going to rewrite stuff at the top because I do need to keep track of the moles of carbon and moles of hydrogen I have because I'm going to use those in a minute. So we were able to figure out that for moles of carbon, I had 0.03747 moles. Moles of hydrogen, we found 0.0749 moles for hydrogen. And I currently know that the mass of oxygen equals 0.5995 grams. The rest of this I'm going to erase because it's no longer needed to solve the rest of the problem. I needed it to get here, but I don't need it for the rest. So I do need to know my number of moles of oxygen. I know I have 0.5995 grams of oxygen. So convert this to moles of oxygen. That cancels out my grams. And I find this to be 0.03747 moles of oxygen. Now I know the moles of carbon, moles of hydrogen, and moles of oxygen. So I'm going to write moles of oxygen up here. I need to find my empirical formula. So remember, divide by the lowest number that we have, and we see that both carbon and oxygen have the same lowest number. If I was to divide 0.03747 moles, divide by 0.03747 moles, and divide by 0.03747 moles, you should find that the ratio is 1 carbon to 2 hydrogen to 1 oxygen. That is your empirical formula. It's the smallest whole number mole to mole ratio. The molar mass of that empirical formula is 30 grams per mole. I know that the molecular form, or the molar mass, so the entire compound, has a molar mass of 180.2 grams per mole. If I take 180.2 grams per mole, I divide that by 30 grams per mole, I get a ratio of 6. What that means is that the molecular formula has a ratio 6 times greater than the empirical formula. So I still have 1 carbon to 2 hydrogens to 1 oxygen for the compound overall, but I need to multiply through that by 6, which gives me C6H12O6. I apologize. And that is your molecular formula. Again, for more practice on this, please see the additional practice for the chapter. I work other problems. I have nitrogen, sulfur, other things in there, so please look through that video, or please actually first try to work them on your own in your notes. They're in your PowerPoint and the student notes. Work those on your own, and then if you're unsure what to do, go ahead and watch the videos.